So moving on to the next speaker. So we will have the next speaker is Thillai Arunthathi. She is from TDMMS College, Tirunelveli, and she attended level O in the 2022 main camp. And her topic is vector subspaces of R, R2, and RQ, R3.
Okay. Now we are going to see about what are the subspaces of R, R2, and R3. So first, we have to know about what is a vector space. Okay. A vector space which is must be non-empty, and that the vector space is a non-empty set which is said to be vector space over a field F if that V is abelian under addition, and for any alpha in the field F and any vector in V, and there is a defined an element alpha V belongs to V and subject to the four conditions, which are alpha times U plus V is equal to alpha U plus alpha V, where for all alpha belongs to V. And the next one is if alpha plus beta times U is equal to alpha U plus beta U. And for all U belongs to the vector space V, and for all alpha beta belongs to the field. Two scalars alpha and beta in the field and the vector in U V, then the alpha times beta U is equal to alpha beta times U. And the last one is 1 into V is equal to V into 1 is equal to V for all V in V. So suppose these all of these conditions are satisfied, then we set a non-empty set V is a vector space over a field F. Okay, right. Now we are going to see about what is a subspace. Okay, and first the definition for subspace. Okay, be a vector space over a field F, and we take a subset W of V, and when we say this W is a subspace, okay, so there are three conditions. The first one is this 0. 0 must be belongs to W, and if we take any vectors x and y in W, and that the addition x plus y also must be in W, and for any scalar t in F and for any vector in W, then the scalar multiplication t in x which must be in W. When these three conditions are satisfied, then we can say that W is a subspace of V. But other many textbooks have not this condition, but they say that a W must be non-empty. But we have used it. C belongs to W, and okay, we are going to see about what are the subspaces of R. And first we take let V equal to R, and W is a subset of V. Okay, now we take some we take an ordered pair x comma y in a W. Okay, suppose like okay subspaces of R. Okay, so we take V equal to R, and W is a subset of V. Okay, now we are going to prove this W is a vector space of V. Okay, but W equal to singleton 0, then this W is really vector subspace, right? Because we have three conditions. 0 must be belongs to W, and we take any vector, any two vector in W, the addition is all must be in W, and for any scalar with any vector in W, the scalar multiplication also in W. So here 0, therefore 0 plus 0 is also must be belongs to W, and 0 in some scalar also in W. Therefore, we can say W is okay. Suppose we take, assume V not equal to singleton 0, and let W is a subspace of V. Okay, then we can say that there exists an X in W, but that X not equal to 0, right? So now we just claim that W must be equal to V. Since uh, since W is a subspace of V, then scalar multiplication is satisfied. Therefore, here a non-zero vector X and any scalar, sorry, here T belongs to R. So any scalar T in R, then T is W. Okay, and okay. Now let y, just one vector y in R, and we can write this y as this term t in dx for some t belongs to R. So we know that the element tx, um, yes, the form of tx is the element is of the form tx is in W, right? So here, therefore, this y is in W. We already know that W is the subset of V, and now we have shown uh, V is the subset of W. That means R is the subset of W. Therefore, we can conclude that W equal to V, right? So, finally, we can arrange this R, and we conclude that the subspaces of R are the singleton 0 and the whole R, right? Okay. Now we are going to see about what are the subspaces of R2. Okay. Let V equal to R2 and W be any subset of V. Okay. And let an ordered pair X comma Y in a W. Suppose that X comma Y equal to 0 comma 0, then it's really vector space, right? Vector subspace. So there are no interesting things. So we just take an ordered pair X comma Y which is not equal to 0 comma 0. So therefore, we can write t times X comma Y equal to tx comma tx is also in W for all t belongs to R, and we know that this is a line, right? So for set of all lines, t times t belongs to R is the subset of W, and now we claim that t times set of all t times X comma Y such that t belongs to R is a line passing through X comma Y and 0 comma 0 is a subspace of V. Is a subspace of V. Okay, so now we have to prove this. Suppose this set of all t belongs to R. This line passing through origin, which is okay. It is a subspace or not. So we can check. So for their existence, R comma S in R, there okay. We can write first. We take two elements in this line in the set, and we have to check their addition is in uh, here or not. So then we take R times X comma Y plus S times X comma Y is equal to Rx plus Sx comma Ry plus Sy, and from that we can conclude that R plus X times X comma R plus S times Y equal to R plus S times X comma Y. So this is this must belongs to W, right? So addition is satisfied, and then now for scalar multiplication. Okay, some scalar t in R and an element in the line R times X comma Y is equal to tr times X comma Y. So it is belongs to W. So the scalar multiplication also satisfies. Therefore, we can say that this line is a vector subspace of V. But now we have to generalize this part. Okay, now we have to generalize this. So we just let an x1 comma y1 equal to 0 comma 0 and another element x2 comma y2 equal to a comma b, and we know the parametric form of the equation of the line, which is x minus x1 by x2 minus x1 equal to y minus y1 by y2 minus y1. Then substitute that point 0 comma 0 and a comma b here. Then we get x by a equal to y by b. So what we have concluded from this, we can say any line in this form is a vector space of V. Yes. So, from this we can say that any line which is passing through RG is a subspace of R2. Okay. Now we have one question. Suppose we take any element, any vector which is not on the line in R2, then what will happen? Okay. Suppose that W contains C comma D in R2, which is not on the line. T times A comma B such that T belongs to R. So then we have to prove these two elements are A comma B and C comma D is a basis for R2. Okay. So now we just claim this A comma B and R but C comma D are linearly independent. So what we have to, their linear combination, we take their linear combinations equal to 0, and then we have to prove alpha and beta equal to 0, right? So alpha times A comma B plus beta times C comma D equal to 0. Then alpha A comma alpha B plus C comma beta. So alpha A plus beta C comma alpha B plus beta D equal to 0. So the one alpha A plus beta C equal to 0 and alpha B plus beta D is also equal to 0. Then when we solving this equation, we get beta times BC equal to 0 and alpha times BC minus AD equal to 0. So suppose this BC minus AD equal to 0, then what we get? That is BC equal to AD, right? So AD equal to A by D. So from this ordered pair, C comma D is written as T times A comma B. But this is the form of line. Any element in the line which is of the form T times A comma B, right? But we take this element C comma D in a line. Okay. So this is a contradiction to our assumption. So therefore the only possibility is alpha and beta equal to 0, right? Okay. Therefore we can conclude that this the vector A comma B on the line and that C comma D is not on the line are linearly independent, and it spans whole R2. So from this we can conclude that any we can choose some vectors which is not on the line, then that subset, suppose that subset of R2 is a vector subspace, then it must be R2. Okay. Therefore, the subspaces of R2s are 0, 0 and line passing through origin and whole R2. Sorry, here comma R2. Okay. So now we are about that subspaces of R and R2, and now we are going to see about the subspaces of R3. Okay, so first we let V is equal to R3 and W is a subset of R3. Okay, so first here, here set of all 0, 0. So 0, 0, 0. This is a origin, right? So 0, 0, 0 is trivially a vector subspace. of R3, right? So we take an vector, take a vector a comma b comma c in W, which is not equal to 0 comma 0 comma 0. Okay, so here also this case also similar to in R2. So here we take then t times a comma b comma c is also in W, right? So this is a line. So now we claim that this is a line passing through origin is a vector subspace of R3. So first we have to prove this is a vector subspace or not. So first we take two elements in this set, T1 times a comma b comma c in W. Sorry, here this set. T1 times a comma b comma c and T2 times a comma b comma c is in this line, and then their addition T1 times a comma b comma c plus T2 times a comma b comma c equal to T1 plus T2 times a comma T1 plus T2 times b comma T1 plus T2 times c. So it also belongs to W for R, T1 T2 belongs to R, and also there is scalar multiplication times T1 into a comma b comma c is equal to alpha T1 times a comma b comma c is also belongs to W for all alpha in R. So we can say this is a vector subspace of R3. Okay, and here also we just generalize from using the parametric form of the equation of the line. So the x minus x1 by x2 minus x1 equal to y minus y1 by y2 minus y1 equal to this equation, and we just here put we take two vectors x comma y comma z equal to 0 comma 0 comma 0 and x2 comma y2 comma z2 equal to a comma b comma c. Okay, so here when we put this equation that vectors and we get x by a equal to y by b equal to z by c. So therefore we can say any line is of this x by b equal to z by c is a vector subspace of R3. Okay. And then suppose we take any vector x comma y comma z not on the line t times a comma b such that d belongs to R, then what will happen? Okay. Let we take an element x comma y comma z which is not on the line. So now we have to prove that these two vectors a comma b comma c and x comma y comma z, this is the basis for these two vectors are a basis. Here R2, this is the basis for R2. Okay, here okay, then we claim that this a comma b comma c and this x comma y comma z are linearly independent. The linear combination, we take the linear combination equal to 0, right? So alpha times a comma b comma c plus beta times x comma y comma z equal to 0. Then from this we get these three equations: alpha a plus beta x equal to 0, alpha b plus beta y equal to 0, and alpha c plus beta z equal to 0. So when we solving this equation, we get alpha times xb minus ay equal to 0, alpha times xc minus az equal to 0, and this beta times yc minus bz equal to 0. Suppose alpha equal to 0, beta equal to 0, or these three xp minus ay equal to 0, or xc minus az equal to 0, or yc minus bz equal to 0. So suppose alpha and beta are not equal to 0 and these three are equal to 0, then we get this x by a equal to y by b equal to z by c. But this is the form of the line. So but we take an vector which is not on the line, so which is a contradiction. So therefore alpha equal to beta equal to 0. So therefore These two vectors A comma B comma C and X, Y, Z are linearly independent and it spans R2. Therefore, this W equal to R2. Okay. Suppose, okay, here R3 we have four possibilities, right? The first one is the dimension 0, which is 0, 0, and for the dimension 1, the lines passing through origin, and for dimension 2, planes passing through origin, right? So we just completed the first two cases, and now we are discussing about the we have to discuss the case which is the planes passing through origin. Okay, so let W equal to set of for X comma Y comma is, sorry, here the bracket is not included. Okay, so here X comma Y, okay, X comma Y comma is such that AX plus BY plus CZ equal to 0. This is a plane passing through origin, right? So we have to prove this is a vector subspace of R3. So we just two elements in W, let AX1 plus B plus Z1 and AX2 plus BY2 plus CZ2, and their addition is must be A times X1 plus X2 plus B times Y1 plus Y2 plus C times Z1 plus Z2 equal to 0. So it must be belongs to W, and their scalar multiplication for any alpha in R, alpha times AX plus BY plus CZ equal to alpha A times X plus alpha B times Y plus alpha C times Z. So it's also include that W is a vector subspace of R3. Suppose we take any vector x1, y1, z1, which is not on the line t times a comma b comma c, and not on the plane ax plus by plus cz equal to 0, which is the line passing through origin. At the same time, it's not in the line the plane passing through origin. Then what will happen? Okay, so we take one vector x1, y1, comma z1, which is not on the line and not on the plane passing through origin. Okay, and now we have to prove that these three are the basis of R3. So first we claim that a comma b comma c, x comma y comma z, and x1 comma y1 comma z1 are linearly independent. So they let their linear combination equal to 0. So therefore alpha times a comma b comma c plus beta times x comma y comma z plus gamma times x1 comma y1 comma z1 equal to 0. Therefore alpha a plus beta x plus gamma x1 equal to 0, and alpha a plus, sorry, here beta y plus gamma y1 equal to 0, and alpha c plus beta y plus gamma z1 equal to 0. So when solving this equation, we get alpha equal to 0 and beta equal to 0 and gamma equal to 0. Sorry, here not type that c by a, or we get c by a equal to z by x equal to z1 by x1, and b by c equal to c by z equal to y1 by z1, and which is of the form that is any vector in that line t1, sorry, t times a comma b comma, therefore which is a contradiction to our assumption, which is not we take an vector which is not on the line. So therefore we can conclude that alpha, beta, and gamma must be equal to 0. So these three vectors are linearly independent and it spans R3. So hence we conclude that the possible subspaces of R3s are 0, 0, 0, and line passing through origin, and plane passing through origin, and R3. Okay. So today we are discussed the subspaces of R R2 and R3. So do you have any doubt? Then ask. Sir?
Okay, you are done, Thillai?
Yes, sir. What, sir?
You have finished your talk?
Yes, sir. Finished.
Vishwajit has raised his hand. Vishwajit.
This like these two elements x comma y comma z and a comma b comma c that was not part of R2 na, so how this, let's see.
Audible, Vishwajit, but your voice is breaking.
So, I'm saying in previous slide we have considered two elements na, a comma b comma c, and we claimed that they were spanning R2. Yes, right here. She told like there should be R2 instead of R3. Right?
Sorry, what?
Like you were saying in the talk, like there should be instead
Yeah,
of R3.
yeah.
Here.
When I am saying, I say that here not R3, here R2.
Yeah, but a comma b comma c, this element, this vector is not so how it can span like these two elements? How the linear combination be equal to R2? Means R2 we take an ordered pair, na? We have elements as an ordered pair. We have here three tuples.
Yeah, you are right. Okay, I think I made a mistake here. So
Okay, no problem, Thillai. No problem, no problem. It's fine.
okay.
Vishwajit, I think Thillai will correct herself.
Yes.
Okay, thank you, Vishwajit. Okay, thank you, Thillai. It was really a good talk. So even if we think sometimes some cases are like trivial, it doesn't, and this shows these trivial cases also require some proof to prove them. Okay.
Yeah, okay.
So Thillai, you can let us thank the speaker again.